is a porous material. And that also has also a very good environmental application, that is an application to water treatment and then soil treatment. Biochar is produced by the pyrolysis of coconut husk at, let's say, elevated temperature. Here we considered 450 degrees Celsius. And then after that, we modified the biochar, and then we look at its antimicrobial and antioxidant effects. Why zinc? We chose zinc because zinc tends to have a broad antimicrobial properties, and also it generates reactive oxygen species, which disrupts cell membranes, and also it has low resistant development. The aim of this study is to synthesize zinc modified biochar, characterize it, and then evaluate the antimicrobial and then its antioxidant activity. As I said earlier on, the feedstock was coconut husk. We dry it, air dry, and then it was put in a kiln and then underwent pyrolysis for 1 hour, after which we use zinc nitrate solution, 5 molar, and then we put in the biochar, and then we perform ion exchange, after which we filtered it, dried it in an oven at 100 degrees Celsius. And then we tried it against some microbial strains and then some fungi. So as I said, the biochar, that's the biochar that we have. Then we grind it into a powder form before the ion exchange. And this is the ion exchange process. The characterization, we characterize it using the XRD, SEM, FTR, and then the antimicrobial test, we use MIC, MBC, OMFC against bacterial and fungal strains. And then the antioxidant assays, we use DDPH and ABTS. From the XRD, the biochar shows an amorphous carbon structure. And after the zinc exchange, the other side shows zinc oxide phases in the structure, but the amorphous structure of the biochar was still maintained, indicating that the ion incorporation was successful and the structure of the biochar was retained. The same also indicates a granular amorphous structure which has partial deposits of zinc pods or coats, but the morphology was more compact, as is shown in the SEM. In the FTIR, we observe that there was some shifts from the FTIR. You can observe some shift in the OH and CU bonds as compared to the raw biochar structure, indicating chemical bonding of zinc biochar. And chemical interaction was really confirmed. But yet still here, the structure of the biochar was retained, only that based on the absorption, we can observe deep peaks at 3171 and then 1762. Then the antimicrobial mechanism is such that the zinc that is contained in the biochar will produce the reactive oxygen species, which will then interfere with the cell membrane and then also destroy it. And the zinc itself would also disrupt and kill the DNA and protein damage to the cells. So from the data, we observed that the raw biochar was not effective. It has no microbial activity. But after zinc exchange, it possessed broad spectrum of microbial activity at MIC or minimum inhibiting concentration of 0.5 milligram per ml, showing a broad spectrum activity. So after the ion exchange, it was effective against E. coli, pneumonia, SRS, typhi, and then the fungus, that's the A. niger, and then the albicans. It shows bactericidal effects. When we look at the R is 1 BC for E. coli. It's also 1 BC for pneumonia, 2 BC for SRS, 2 BC for typhi, and then the fungus 2 BC, and then 4 BC. You can see that it was actually less potent comparatively to albican, and this might be probably to the cell structure of the albican. But generally, you can see the antibiotics that were used was more superior, but in terms of SRS and the typhi, the zinc exchange biochar was more effective than the tetracycline, which was used as the control. So in effect, we can say that the zinc exchange biochar exhibited strong microbial activity. Then, in the same vein, the antioxidant activity, that is scavenging of the coconut husk biochar, in such a way that it has to reduce oxidative stress. So from the experimental data, when you look at the zinc exchanged biochar, the raw biochar itself also showed some antioxidant property. That with the DPPH, the initial concentration was 60, that is at 5 milligram per mole. It was 60 for the raw biochar, but for the zinc exchange biochar, it was somewhere around, I think, 65. But we can see that beyond the 5 ml, the 5 mg/ml, all the concentration tend to decrease. And this might be due to agglomeration of the biochar particles, since it is not that clear. So maybe there was agglomeration, and that might be the cause. So here, the concentration is, but when it comes to the ADTS, here also we observe that the raw biochar was less potent compared to the zinc exchange biochar. So in effect, when you compared all these to the what called the vitamin C, which you see that the vitamin C showed very high antioxidant activity, and that is expected because that one is tailored for that particular function. So as I said, DDPH, the zinc was approximately 67% inhibition, which was better than the raw biochar, but also it shows a concentration dependent. In the ABTS also the same thing, the zinc exchange biochar showed an inhibition of 57%, higher than the raw biochar, indicating that the zinc really played a role in it. And it also shows a strong concentration dependence. What can this be used for? So from this study, we can see that the zinc modified biochar can be used for water treatments. It can also be used for surface disinfection, and it can also be used for agricultural purposes. From the study, we conclude that, yes, the zinc modification really enhanced the biochar, giving it a dual antimicrobial and antioxidant activity. And we agree that this will be a very sustainable material that has prospects and might have many health benefits. So in future work, we are really going to look at the, we want to scale out the studies, then to look at the toxicity effects and do real environmental testing of this material. Thank you.
Thank you very much, Ralph. That was very interesting. I was a bit concerned in the beginning that you were going to propose that people eat the stuff. That's not the case, is it?
No, no.
Okay, so and when you do water treatment with this material, there's no residual toxic effects left in the water.
Well, that will be determined because the biochar will be a slow release. We don't think there will be any toxic effects in the water. So of the zinc.
Okay. And okay, so how did you measure the antioxidant activity?
We use a photospectrophotometer to do that. We set it at a particular frequency for that test, and that is how the measurement was done.
So what do you oxidize? So what is the complete assay?
That's I don't have it in my head exactly. This was a teamwork, and it was done by the team. So they prepared the DPPH assay. I don't have it clearly in my head right now.
Okay. Okay, thank you very much, Ralph. Does anybody want to ask a question to Ralph? Anybody that's online at the moment? Okay. Okay, well, with that then, we'll thank Ralph very much for his presentation. I'm very grateful that you attended the meeting and that you presented your work. It's very interesting, and good luck with the continuation of the studies.
All right, thank you.
Okay, so the next talk is, we're a little bit early for the next talk. So we're actually 10 minutes early. I see you, Sinasipo, you're here. The next talk is from Sinasipo Palazzo, who's now been made a co-host. So you can stop sharing your screen now, Ralph.
Okay.
And Sinasipo, if I can ask you to share your screen. Okay, we can see your screen now. Um, I'm going to wait. I'm going to wait for a few minutes, Sinasipo, if you're happy with that. Can you speak? Do you want to go into presenter mode? Yeah, well done. Okay, we're ready to go. We'll just wait until past.
Am I audible?
Your audio is fine, and we can see your screen nicely. But you're 7 minutes early, right? So I'll wait until we scheduled to go at 11:30.
Okay.
What questions?
Yeah.
What? Thank you.
Oh, c'est contribution pour vous soir.
Okay, let me introduce Sinisipho Palazzo. He's from the University of Johannesburg, and thank you very much for putting in your abstract and for giving us this talk this morning. He's going to talk about in vitro characterization of electrospun nanofibers for chronic diabetic wounds. And I think you can go ahead, Sinisipho. Thank you very much.
Thank you very much. Am I still audible?
Yes, you are.
Okay. My name is Sinisipho Palazzo. I'm a master student at the Laser Research Center of the University of Johannesburg, South Africa. And today I'll be sharing a section of my work, of my master's work, entitled In Vitro Characterization of Electrospun Nanofibers for Chronic Diabetic Wounds. This work is done under the supervision of Prof. Satish Kumar and the co-supervision of Prof. Nicolette, both of the Laser Research Center. Diabetes mellitus is a metabolic disorder where the body cannot produce or effectively use insulin, resulting in a constant state of high blood, also known as hypoglycemia. Currently, in adults which is the age 20 to 79, 11% of that population currently is living with diabetes. To give perspective, that's 1 in every 9 adults has diabetes, according to the statistics. And this number is expected to increase by 45% by the year 2050. And even more alarming, Africa is expected to contribute around 142% of this detrimental increase, which is very alarming. I'm hoping we're going to have another COVID-19 type of miracle. One of the complications of diabetes is diabetic foot ulcers, which are ulcerations that form normally in the lower extremities of people with diabetes due to the damages caused by a chronic state of hypoglycemia. Now, in diabetics, there is a 19 to 34% chance that they will develop diabetic foot ulcers in their lifetime. Even more alarming, there is a statistical link between diabetic foot ulcers and limb amputation especially in diabetic people. 85% of those amputations are preceded by foot ulcers. Medical intervention to this problem has been standardized for the most part, which includes mechanical offloading to relieve pressure of the common sore points, and in the wounds, debridement or removal of the dead tissue, and infection control, vascular restoration, and wound dressing. In the overall scope of the project, of my master's project, we mostly focus on 2 sections, which is the infection control part and the wound dressing part. With the infection control, with research has been shifting away from the use of antibiotics due to the rise of resistance towards more natural forms of antimicrobials, which can bypass the pathways that trigger resistance in microbes. But mostly but this presentation is mostly focused on the wound dressing part. So traditionally, wounds are dressed with gauzes, cotton wool, bandages, and adhesive plasters. Now, these are affordable, thus accessible. However, they are passive in nature, meaning they are only effective in protecting and isolating the wound environment. Outside of that, they have no functionality. And they have been reported to dry out the wound, and they require frequent changing. And during the frequent changing, they may result in secondary wounds. Thus, research has been focusing on more advanced form of dressing materials. These include nanofibers, hydrogel dressing, foam dressing, and alginate dressing loaded with the necessary chemicals. Now, these advanced wound dressing, compared to the traditional forms, they are less affordable. However, they are more active in terms of addressing the specific issues that are associated with these type of wounds. And they can be tailored to maintain an effective wound environment depending on the formulation process. And they can be left for days. In some cases, they're expected to self-degrade when they're in the wound. And they can also be tailored to the environment to respond to environmental clues such as pH and temperature. Which brings us to the aim of our study. We aim to formulate nanofibers using electrospinning. We chose two polymers, gelatin and PCl, polycaprolactone. Gelatin is a natural polymer. PCl is a synthetic one. Gelatin has cell interactive activities and PCl has the mechanical part. So together they form a better complement. So upon formulating these nanofibers, we will then assess their morphological and mechanical properties in relation to supporting tissue regeneration. So we wanted to confirm their formulation through imaging, determine their size, shape, and alignment, and we aim to analyze their chemical component, as well as to assess their fluid management through a multitude of tests, which I will expand on later on, and then to confirm the cytocompatibility for this section. This image provides an overview of the study we have been carrying on, starting with the preparation of solution using the two polymers, which we dissolve in glacial acetic acid until it formed a uniform solution. We took that uniform solution, we put it through the electrospinning process, collected the fibers, and then we used the fibers for characterization studies through FESM imaging and FTI spectroscopy. We also evaluated their biological effects on the cell, most importantly, their ability to interact with the cells successfully. And we also did physiochemical performance studies through water uptake ratio, porosity through the ethanol displacement method, as well as water vapor transmittance. Our results based on SAM imaging confirmed that we did indeed formulate nanofibers, and they were continuous, meaning they were not fragmented and broken, and they were beard-free. And the nanofibers had a random alignment due to the collection method that we used. We used a stationary collection method, which is a part of the electrospinning process. And the fibers had a smooth surface with an average fiber diameter for this particular sample of 357 nanometers, which is within acceptable range. Through FTI, we wanted to confirm that the polymers that we use did in fact chemically interact with each other and are not just sitting next to each other in the fibers. So they are functional groups. So the lower bottom indicates the FTI spectroscopy of gelatin, pure gelatin on itself, and the one in the middle for PCL, and the one on top for the nanofibers, which are a combination of both. And as you can see, let me point this here. This is a major peak for gelatin in this test. As you can see, it's translated to the nanofibers, as well as this minor peak here for PCL is showing up on the fibers. But most importantly is this peak right here, which we expected because according to literature, this carbonyl group stretch of PCl, when it interacts with gelatin, is likely to have this shift and lower in intensity, which shows that it actually binded. So again, this confirms that there is a chemical interaction between our polymers. Our cell attachment studies were also imaged through FSM. They show that the fibers, the cells could attach to the fibers, and the cells attached to the fibers, as you can see here, they had elongated ends and they were flat in nature, which shows that they had a good cell adhesion, which confirms cytocompatibility at this stage and possibly the ability to support cellular growth. The distribution in this case was 7 to 10 per 120 micrometer squared of the nanofibers. Our water management studies results through water vapor transmission rate, water uptake rate ratio, as well as porosity test. Starting with water vapor transmission rate, we had a transmission rate of 7.80 milligram per meter squared per hour. Now, this is slightly below what we expected to get with this type of material. However, looking at the average slope, this is where our good news are. If you look at the graph itself, it's constantly slanting towards the lower mass at a constant rate, which is good because it tells us that our fibers first off have connected pores. That's why they have the ability to lose the vapor, and secondly, that during them transmitting the vapor, they themselves don't degrade because of this average slope here being constant. So they are breathable and they don't degrade in the process of exchanging vapor material. Then our water uptake ratio study showed us that the fibers first off can absorb up to 12 times its initial weight within the first hour. And then they kind of became stagnant after that. They became stagnant, they weren't taking more and they weren't losing water. But the good thing is they were also, see if you look at here, this is barely any decrease. So it means they remain steady throughout. They don't break down when they uptake water, which is a very important function in this. But the overall picture of this is that they are absorbent in relation to exudes in wound environments. And then our porosity tests showed that the fibers were about 52% porous, which if you consider the intent behind these fibers, it's for wound healing purposes. A higher porosity means a greater exchange of oxygen and stuff like that, and the other material that needs to be exchanged. And then a lower porosity means an increase in strength. So something that's in the middle is relatively good in this case, because a higher porosity might have more pores, but structurally it becomes weak, and in the lower, the porosity is lost. Pretty much turns into gauze all over again. Thus, well, it brings us to the end of this section with our FESM analysis addressing the objectives and providing us details on the size, the shape, and the alignment. FTI analysis confirming the blended interactions instead of them sitting next to each other. It has also allowed us to analyze the texture and validate cell attachment, while the water management studies show that our fibers were relatively porous and they had a high water uptake capacity and a moderate to lower water vapor transmission rate, which brings us to simultaneous studies that we are currently running, including cytotoxicity and our drug studies, which bring the whole picture into a complete view. Unfortunately, we couldn't bring those results to this current presentation due to them not being ready at this point. I would like to acknowledge these bodies, the Laser Research Center and the funding bodies, NRF, SACHI, and the Department of Science and Technology. Thank you very much for listening.
Thank you very much, Sinisipho. I'm very pleased that you kept to time so well. We have time for questions. I see you getting a few taps. Does anybody want to ask a question immediately? I have one if nobody else has one, which is why is there such a large amount of diabetes in Africa? Is it not a major public health problem?
If I'm hearing you correctly, you're asking why is there such a large amount of diabetes in Africa?
Yes.
Yes. I'm not 100% sure on the data, but I can assume there's a correlation between the diet currently and the rise in diabetes. We've over the years we've had more fast food options, and mostly of if you look back in time and coming towards most of our diets now don't come from the house where it's cooked meals, just like it was back in the day. Now it's more takeouts and unfortunately the cold drinks. Every lunch, breakfast, and dinner is had with a Coke or something similar with the sugar. So I think that's where the link is.
Okay, so to get back to the topic, does anybody have a question about the wound healing properties of spun nanofibers? Okay, well, thank you very much, Sinisipho. There was obviously a very clear and explicit discussion.
I actually did have a question.
Oh, okay. Well,
Is it possible to, hold on, thing fell out. Is it possible to recover the used material and do titers of antibodies and other sort of markers of cell death?
Could you please repeat your question?
So of the materials that are applied to a diabetic wound,
yes,
can you recover them post-use and look for markers of cell death and immune responses and other things to sort of get a look at, I guess that is one window into what is the effect of the material from a histological and an immune response, because presumably the material, if you look at the wound itself, the wound is healed, so that's not so good from what I'm getting at. I'm going to look at what immune responses and what are the cell biological sort of effects of the material itself. Does that make sense?
Yes, it does. The material itself can be recovered depending on the purpose of what it was used for. The same way at a certain stage you would remove gauze or a cotton ball. You can recover the material the same way, unless the intention is for it to be embedded until the wound heals. So then it will be part of the system according to research, and then it will be broken down and it will leave the body in some in the same excretion method. So with the markers being able to tell the effect at cellular level, I think there has been studies already focusing on the immunological aspect of these materials. I don't know if I addressed your question.
Yes. And so that will be interesting if you are able to go to clinical trials or in animal models to do that, to sort of see what is the, I guess, wound debris and antibodies or whatever, cytokines or whatever that are in.
Yes, yes. There are studies on animals. There are animal studies, papers published on animal studies. I'm not sure to the extent at which they went to obtain this particular information that you're asking for.
Okay, thank you.
Thank you.
Okay, so thank you very much, Sinisipo. Please, will you unshare your screen, and will you, Lawrence, make Fazili Matsweni a co-host so that he can share his screen?
We are in the same room, so I'm just going to switch to his slides.
Okay, thank you.
Good morning, everyone. Can you guys hear me?
Wait, how do I exit this?
What are we doing on the screen sharing? So it's the same computer? Should I not? What should I do?
Yes, it's the same computer. You open
Okay.
yourself.
So
Okay. Hi, Fazili. Will you put your screen? There we go. Okay. So the next talk is also about wound healing, and in this case, we're looking at the physicochemical characterization and antibacterial properties of cerium oxide nanoparticles. So, Fazili, if you would go ahead and tell us all about it.
Good morning, everyone. Am I audible enough?
Yes.
Okay.
Yes, you can. You're fine.
Good morning, ladies and gentlemen. My name is Fazili Matsweni from the University of Johannesburg, and my study that I'll be discussing is the physical chemical characterization and antibacterial activity of cerium oxide nanoparticles. This is supervised by Professor Satish Kumar and co-supervised by Prof. Heidi Abrams from the Laser Research Center in Johannesburg, in the University of Johannesburg. Now, adding on to what my colleague has discussed before, I would say that imagine a disease that affects millions of individuals between the ages of 20 to 79 and silently result in heart disease, kidney failure, and blindness. Now, in addition to this is what chronic diabetic wounds normally result in, right? As my colleague has also said, that they have a high prevalence rate, affecting more than 500 million individuals globally. While noting is that diabetic foot ulcers are the most common type of chronic wounds associated with diabetes, which are mostly looked upon, in which more research needs to be looked upon other parts of the body, including the blindness and minor wounds, mostly on hands and other parts of the body. One thing that most people would have to note is that these diabetic wounds have a high prevalence of creating biofilms resulting in bacterial infections. Now, these mostly result in an alteration in the blood glucose pH, reducing the immune penetration within cells. This causes prolonged inflammation and oxidative stress in the long run, resulting in a longer wound healing period. Additionally, there is mitochondrial dysfunction and ATP growth, meaning that various cellular models and mechanisms, including your proliferation and angiogenesis, which assist new cell growth and healing, are normally inhibited. If not inhibited, they are normally delayed over a period of time, if not restricted. Furthermore, diabetic wounds also have a high frequency of reducing the oxygen levels within cells, and also basically reducing or damaging the lipid membrane within cellular tissue, including the ones in veins, resulting in diabetic neuropathy. Now, moving on to another thing is that there has been a high level of bacterial infections, mostly resistance. Another type of bacteria that is mostly looked upon at the moment is Anita-Bacillia, which is one of the most bacterias that are mostly carbapenem resistant, which is the last phase of antibiotics. Now, in this study, we are looking at Pseudomonas aeruginosa, right, which is a rod-shaped bacteria which can be found in both anaerobic and aerobic conditions. This bacteria has a high mortality rate or high prevalence across the globe, as it is ranked basically ranked fourth in the world as the most mortal or basically deadly bacteria, mostly causing amputations and other illnesses, including gangrene. Moreover, in South Africa, it is ranked fifth, as the fifth highest, apart from the Staphylococcus aureus and other bacteria, meaning that it is slightly increasing at an alarming rate. Most of those bacterial infections are mostly found in diabetic wounds, which is what we're focusing on, burns, and also other traumatic injuries, including venomous ulcers. Their form of mechanism when it comes to antibacterial resistance includes their carbapenemase enzyme resistance, which blocks the penetration, and also absorption of antibiotics, which these carbapenem antibiotics are the last phase of antibacterial resistance, which are now being prone to basically there are high cases of antibacterial resistance. Other forms would include the biofilm inflammation and the efflux pump, which on various mechanisms result in bacterial proliferation and inhibition of the drug penetration, or otherwise, I would say that they reduce the healing of the wound. Now, for this study, we are proposing the use of serum oxide nanoparticles for the wound healing, and also looking at the antibacterial application. We chose this because we know that serum, it is a lanthanide atom, and it is a rare earth metal that is basically increasing in most studies, being looked upon as having the effect of increasing the wound healing process in all the 4 phases of the wound healing process. Another thing is that when used with secondary metabolites in green synthesis, which is an approach that we're looking upon, it has the ability for it to shift between its serum 3 and serum 4 ions in various mediums, bringing the cerium oxide nanoparticles to a high or enhanced stability. Another thing is that these cerium oxide nanoparticles, they have both and they promote antioxidant, anti-inflammatory, and proangiogenesis effects, meaning that they accelerate the wound healing process without resulting in any cytotoxic effects. Moreover, we have seen that they have antibacterial properties, which causes electrostatic cell membrane damage, and also they inhibit bacteria, they inhibit protein and DNA synthesis produced by bacterial cells. Now, more in detail, when looking at the aims of the study, we looked at about the characterization and antibacterial efficacy of the cerium oxide nanoparticles. This was looking at the rationale faced by both metallic and lipid-based nanoparticles, which have been shown to have various cytotoxic effects, which are mostly dose-based and dose-based and material-based in the terms of wound healing or wound healing studies. Looking at our synthesis method, we looked at an up-down method of creating the cerium oxide nanoparticles using a plant extract, mostly leaves from a plant which I cannot disclose at the moment due to ongoing investigation. From that, we were able to formulate the nanoparticles and also looked and characterized them through various techniques, including your UV spec, which looks at the surface resonance, FTIR, which looked at the elemental composition, zeta potential, and also FESIM, which is basically the morphological analysis of the nanoparticle. We then moved to the antibacterial study, whereby we first looked at the minimum inhibition of these cerium oxide nanoparticles, moved on to the dose diffusion, and also used microscopy to look at the cell membrane damage within the bacteria as a method of inhibiting the bacterial growth or proliferation over a 24-hour period. Furthermore, we looked at our cellular compatibility studies using microscopy, mostly light microscopy and fluorescence microscopy, to see if the nanoparticles were less toxic or they could actually induce basically induce.
Sorry, can you just stop for a minute? Somebody else is starting to screen share on top of your display.
Okay.
Hold on 1 second. Who is doing that? How is he doing that?
Isaiah.
Okay. Well, at least we stopped that.
Okay, so you back. Can you see your screen, Bazili?
Yes, I can see my screen at the moment.
Okay, so now you're back to your slideshow.
Okay, can I carry on?
Yes, please carry on.
Okay. Oh, as I was saying that we looked at the cellular compatibility using both light and fluorescence microscopy to determine if these nanoparticles do enhance and induce our cellular wound healing. Now, looking about the results which we looked upon, selected for this presentation, we looked at the UV spectroscopy, and when formulating our nanoparticles, looking at figure A on the top left-hand side, we saw that when synthesizing our nanoparticles, a peak showed between a 375 350 and 375 nanometers, showing the basic synthesis of the nanoparticles that had been formed. This was good for our study because these nanoparticles mostly also interacted with the plant extract within, as you see, between the 250 to 300 nanometer range, in which they show that the peaks, basically the peak tendencies also shows that they were interactions and also a green synthesis formulation. We then looked upon using our looking at the surface morphology using FECM, using a dried method. Yes, using a heat-dried method, in which we saw that the nanoparticles had a uniform shape, although there is the gloomy. Although the picture also shows a gloomy or water-based hydrated aggregation, we saw that this was mostly caused by the heat process of drying our nanoparticles. Furthermore, we also look at the elemental composition shown in figure E, and we saw that cerium and oxygen were mostly one of the important elements showing the successful synthesis of these nanoparticles. Other elements including sodium, chlorine, and sulfur. These were some elements which were found on the glass slide, and also parts of the plant extract that we used, showing that they reduced basically their reduced peak, or basically quantity, showed that these nanoparticles did not degrade over the process of synthesis and during the analysis process. We also looked at the comparative FTIR, looking at the elemental composition, right? In this, we saw that the broad peak at the broad we saw that the hydroxide stretch vibration between the 3,500 nanometer wavelength range showed that there had been hydration between our nanoparticles, which is also shown in the drying out as shown in figure 3. Another thing that is worth noting is that during the green synthesis method, between the peaks of 500 to 1,000, we saw that there was a presence of the organic capping, just in which the cerium oxide binded to the plant extract, causing the successful formulation of the cerium oxide nanoparticles. Moreover, we saw that there was a reduced we saw that there was a reduction in oxidation formulation in this, meaning that we also saw that there is the capability of the cerium oxide jumping from a cerium oxide 3 to a 4 ion-based exchange. Another thing that is worth noting is that is rarely found in cerium oxide nanoparticle is the peak which showed the alpha and beta unsaturated ketones, which this is rarely found in cerium oxide nanoparticles, but mostly found when creating under green synthesis method, basically when formulating the nanoparticles using a plant extract, meaning that these nanoparticles were formulated successfully. We also looked at the crystallinity of our nanoparticles, in which we saw various peaks at 111, 200, and 220, which also showed that the nanoparticles forms were actually crystalline in the sense of the wound healing process. And looking at our looking at our future wound healing studies, this will be beneficial as we know that the nanoparticles will not degrade, or basically will not degrade easily over time. Okay, and then we also looked at the antibacterial properties of the nanoparticles formed and the cellular compatibility in this instance, whereby we looked at using a PI stain, which only stains the membrane damaged antibacterial and membrane damaged bacterial cells, in which we compared this with our control antibiotic, which was tazobactam, right? And when we're looking at this in comparison to the plant extract alone, which is Pseudomonas aeruginosa, and the nanoparticles we formed, the nanoparticles formed had a higher, basically, yeah, they had a higher percentage or a higher rate of resulting in membrane damage, as you can see in figure C, in which most of the bacterial cells were able to absorb the bacteria, and they were able to absorb the nanoparticles, resulting in their membrane damage, and also their fluorescence basically emitting the red stain over time, over the 24 hours. We also looked at the compatibility or cellular compatibility using BJ25 for cells, and we saw that over a 24-hour period, there is an increase in the viability treatment. Moreover, looking at figure E, we also looked at the cellular morphology, and we saw that in comparison to the control group, the concentration-based treatment in comparison to the MIC that we received for the antibacterial studies had basically showed minimal to no cytotoxic effect on the cells at both 24 and 48 hours. Moreover, we also looking at the localization and also the nuclear morphology of the fibroblastic cell, looking at whether the serum oxide nanoparticles formed were actually toxic or where they are localized within the cells, right? Looking at the figures shown on the left, in comparison to the control group, we saw that there was no nuclear or basically membrane, nuclear morphological changes due to the serum oxide nanoparticles. Another thing is that the nanoparticles highly interacted with the nucleus without forming any cytotoxic effects on the normal cells, and without forming on the normal cells that we used. Moreover, in comparison to the standard metallic nanoparticles, which we are still looking upon, we saw that their dose response in some cases, they do show a change in the morphology when used at high concentrations. And also, looking upon the right on the overlay using the mito tracker, we saw that these nanoparticles are also located, basically they do localize in the mitochondria of the cell, right? Meaning that during wound healing phases, they can enhance the ATP, resulting in a high viability and also proliferation state, in which there is more accelerated wound healing process for our study. We also looked at the RGB fluorescence we also looked at the RGB fluorescence profile of this, and this showed that the nanoparticles that we used for the study basically over time they were more compatible to the cells. I can say that they were more compatible to cells, and also in quantifying the amount of nanoparticles absorbed by the cells, we could see that a higher percentage was absorbed. In conclusion of the study, this portion of the study, we saw that the nanoparticles formed basically had a dose-dependent decrease in the cellular viability in comparison to the damage shown by the bacteria. Overall, additionally, they had a good physiochemical properties, meaning that they will be able to last or basically be stored over long periods of time, which we also have done using our zeta potential and other methods, which are just not shown in this study. And also looking at the cellular compatibility, we saw that there were basically these nanoparticles had the ability to induce both the wound healing in both normal and diabetic wounds, meaning that when moving on to animal studies as future studies, we will see beneficial or basically good results in the long run. Thank you for the study, and these are the funding bodies which I'd like to acknowledge, including the University of Johannesburg, NRF, SACHI, Laser Research Center, and the Leica microscope for allowing us to use their microscope in imaging our images. Thank you very much.
Thank you very much, Fazile. Unfortunately, you are 6 minutes over time, so
Yeah.
I'm not going to allow questions. I don't see any hands up. I did actually have a question. Maybe I should ask it. To what extent are the antimicrobial properties due to the plant extract, and to what extent to the cerium oxide?
So basically, as I understand your question, say to what extent, meaning that how far does what are the antibacterial effects of both the plant and the cerium oxide nanoparticles formed?
Yes, are they separable?
Yes, they are separable because when looking at the plant extract alone, it does cause antibacterial, it has have antibacterial properties, but these are limited. And also when absorbed by the bacteria, in most cases, a small amount is absorbed by the bacteria over a long period, meaning that in instances whereby there are chronic wounds and other types of wounds, they have a limited ability, or yes, a limited ability to cause the what do you call this, the bacterial damage or bacterial inhibition. Now, when looking at the cerium oxide nanoparticles that we did, they were more effective because there is a diffusion study that we did in which nanoparticles and the controlled antibiotic that we used had similar results. Basically they showed similar results in inhibiting the bacteria growth.
Okay, thank you very much, Fazile. Please, will you stop sharing your screen, and we'll Sishle Tibeti, who's going to talk next, please share your screen.
Okay, no stress. Please, can I do this? Has it stopped sharing?
Stop sharing. Please stop sharing.
Yes, you stop sharing.
Okay,
And
it has.
Sishle Tibete is ready to share.
Sishle,
Okay.
are you ready? Are you ready to share? Okay, okay. So the next talk is from UCT. It's Sishle Tibeti, and he's going to talk about insights into structural analysis of caffeine oxalic acid co-crystals using high-resolution PXRD and computational refinement. It looks like a very interesting talk, so go ahead, Cecily, if you go into full screen presenter mode. Thank you. Thank you. All ready to go. Okay.
All right. I just want to confirm if I'm audible before I begin.
Yes, you're perfectly audible, and I'm going to have to run you over time because we're starting now. I'm going to give you your full 20 minutes, but we're starting at 12:20, and so you'll get your 20 minutes. Please keep
Okay,
the time.
thanks so much. Okay, thank you. As I've been introduced, my name is Sihle. I am from the University of Cape Town. I am from the supramolecular group in basically crystallography and physical chemistry, but this is a model for the project that I am currently on for my PhD. It's supervised by Dr. Mohodi and Professor Mino Kaira. This is sort of like an overview from this very great research paper where they talk about the many possibilities one could obtain from crystal engineering of like maybe known or even new drugs that they uncover. And one of the processes that is currently on a high is this step here in the middle. I'm not sure if I have my pointer on. I should, yes. It's this step here in the middle where there is crystal engineering. Usually you can get by just making your forms, like maybe your two multi-component forms, and then you just go straight to reassessing their potential in like pharmacological studies or everything like that, and you wouldn't really know what's the formation of like within those multi-component forms. And this is where our study is based for the most part. So one of the aims of this research work is to synthesize these multi-component forms. I'm going to use the word co-crystal a lot here, but these could be salt forms or they could be inclusion complexes. So that is another concept of work where you can have cyclodextrin inclusion complexes. So it's a cyclodextrin that acts as a host, and you'll have your drug, and then you have to infuse that drug into your cyclodextrin host, and that also changes the pharmacological properties of your drug of interest. So for the purposes of this crystal engineering process, you can determine the structure. I think these are like the main concepts that I think I would refer back to at a later stage, that you want to be able to determine the structure, the lattice structure of this multi-component system. And one of the problems with that is it is very difficult to obtain single crystals, because for many people who are aware of crystallography, they know it as single crystal crystallography. So you need good quality crystals for that. They need to be the right size for that, and you need to have a machine that is going to be good enough for. Fortunately, most of the single crystal machines that are produced now, even maybe the last 10, 20 years, are good enough if you have a good quality single crystal. The unfortunate part is that that doesn't happen most of the time. So most of the time, what you would have would just be a powder sample, and you have to hope that it is crystalline so that you can be able to determine the structure via a PXRD. And you would just go to how you validate your structure with computational tools and also thermal analysis. So I think I've sort of highlighted this slide in my previous slide, but the potential of co-crystals or multi-component solids is very vast. You can look at it from this direction. This would be your active pharmaceutical ingredient. So it could be any drug that you've just synthesized, or anything that you found interesting, and maybe you found you don't like its solubility and you kind of want to mess around with that and maybe make it more favorable. And then the co-former could be anything, your small small dicarboxylic acids like oxalic acid in this instance, or your amino acids, or any other form of your neutral molecules. You could use that as your co-former. And one of the major problems or major things that I want to highlight that guide this process, the formation of these multi-component systems, is the hydrogen bonding and pi-pi bonding. So you would find that in many discussions, the conversation is around hydrogen bonding more than the other intermolecular forces. And that is due to the influence of hydrogen bonding compared to everything else. So you would find that this is what is highlighted in those discussions. So like I've mentioned, you can manage or change the stability, the solubility, and critically the bioavailability of your drug of interest. And this is very important because this what determines how well the drug acts once it's in the system, or once it's within the body, or the target area. So I think most of you will be aware of caffeine. Maybe most of you have already had your caffeine for the day. So some would be aware of that. It has very limited solubility in water. You would need to heat up water for it to dissolve. If you put water in room temperature and you try to mix it, it doesn't really dissolve that well. And oxalic acid is just a small hydrogen bond donor. So here it's used as the co-former, and caffeine is the API. So what we want to be able to investigate from co-crystallization is the hydrogen bonding motif, and also understand if it forms a salt or it forms a co-crystal, and that we can understand by looking at if there's a proton transfer or not, and also look at the solid state properties like stability and dissolution. So this is just a rundown of the methods. You can generalize this, or you can treat it as is for this work, but you basically can do the synthesis by any means. Like you can just do dry grinding, or you can do liquid assisted grinding to form your co-crystals. But in this case, I dissolved caffeine in water and then heated to 77 degrees for 6 hours while stirring. And then you can, I added the oxalic acid to the aqueous mixture. I want to mention that here, what you're trying to do is just form the hydrate. You can try to skip through that process, but managing the hydrate is usually very difficult because you would be messing around with the hydrate in water. So it kind of gets messy. And also when you try to do thermal analysis, as I will show later, it becomes a bit more complicated. And the next part would be to confirm whether the thermal, the dissociation profiles match those of your starting materials, or you form something new. So you can do thermogravimetric analysis and DSC for that. And then you collect from the dry powder that you formed there. Then you can collect your preliminary scans, maybe on like a simpler machine, like a D2, Broca D2, PXRD machine. And then you collect your more robust scan once you've confirmed that. And then you can use any of these tools to do structure solution. So you can use Topaz, EVA, or Expo, and Dash. I pretty much use all of them because they offer different levels of complexity. So to just highlight, this is one of the problems that you would likely have if you're using a simpler machine like a D2. So you would have peaks that usually at lower angle, the theta angle, they look okay. But if you go higher up, they just get muddled with the background. So you kind of want to be able to vary how you look at the pics. So one of the cool things about the D8 advanced machine is that you can do variable scan count. So at higher angles, you just count longer, and at lower angles, you count for a shorter time like you would a normal PXRD machine. And then you look at it improves the secret to noise ratio, and also you can detect weaker reflections. So just to sort of run through the structure determination, once you have your good or decent level of decent level quality of your PXRD, is you do your indexing. So you can do this with any of the software that I had mentioned, like your Topaz, and then you do simulated annealing, and then you do refinement of your simulated annealing. So those are the 3 steps to actually like finding the structure, the lattice structure. So with indexing, what you are only looking for is just the lattice parameters and the possible space group. So you get your powder, that's the only input that you put is your powder pattern. And yeah, this is where ingenuity is actually required a lot in terms of the space group possibilities, because you would maybe know that your 2 starting materials are both they both have rigid stereochemistry. So that has to guide you to the possibilities of your space group selections. Yeah, so the simulated annealing step is just trying to, so what you would get from lattice structures is just the box basically. And then when you go to simulated annealing, that's when you kind of like have to assign the atomic positions and orientations of your starting materials. So when you do indexing, you don't really need to know the actual structure. Maybe when you're doing like space group assignment, maybe, but for the most part, it's not really a big requirement to know your starting structure. But when you start to do simulated annealing, you need to know the actual number of molecules and all of that. So these are some of the results. So these are thermal results, and if you can observe this black curve here, so this just shows there is no dissociation before around 200. So this is a confidence builder towards maybe hydration. So you would know if you were to do your scan and this clean, that you have no hydration curves, you have nothing around the hundreds here, maybe your water and everything, and he says it was water. So you don't have that. So that's the first step that you need to be certain of. And you can also compare it with your starting materials here. And then as you can see, it's not really the same curve. So you know this is not the same thing as those two. So that is the first thing that you kind of have to be aware of. And then the next part is preliminary PXRD, and as you can see, it's ran until 40. So you just match the 2 patterns, the 3 patterns, your starting materials and your actual product that you formed. And then, yeah, so you look for overlaps and you try to justify them if there are any. And as you can see, this is quite clearly not the same thing as any of these starting materials. So this gives you confidence to then run maybe a VCT scan to probably like 70 degrees or something. So when it came to indexing, I did my indexing with Expo and Dash because I like to use both of them. They offer different levels of flexibility, and these are the starting index lattice parameters that I obtained. I'd just like to mention that if you were to go to a paper that I'm going to share soon or going to go to soon, you recognize that the C parameter is very high on that paper compared to the one that I'm presenting here. And that comes as one of the issues at some point. I'll go to it. Okay, so this is the paper that I was talking about. they're trying to modify the hydration of caffeine using oxalic acid. But in this work, they do it through single crystallography, single X-ray crystallography, sorry. But the main thing that I want to point at here is this. So in this case, you can see this is like a model with a dicarboxylic acid. So it could be anything really. So what they point out are these heterocentrons here, that you can have the hydrogen bonding between the nitrogen and the hydrogen of your dicarboxylic acid, and then you can have another hydrogen bond between the oxygen and that end of the double bond there. And if you observe in this structure that we obtained, is that you do have this hydrogen bond over here, but you do not have that second hydrogen bond, which would be there to that or here to that double bond there. So that is one of the things that we observed, that the hydrogen bonding that we had found was partial compared to what we would have expected. I want to point out that when you do this simulated annealing and you find these results, you might find that when you check your Pauli agreements, so you look like at your profile chi-squared and you look at your Pauli chi-squared, you realize that they do have an agreement. So this is not a highly implausible structure, but once you look at it in greater detail in analyzing the hydrogen bond network, you actually realize that this structure is not quite correct. So the final step that we attempted was the refinement, and in refining, what I want to mention a lot is if you do refinement, most of the time it does not change the starting structure in that great of a detail. It might improve the hydrogen bonding network, but in this case it did not. We came up with pretty much the same thing, but it did change some of the atomic positions a bit, and it's sort of like changed the packing arrangement towards the higher C that I had mentioned earlier, because in my instance, the C value was around 4 and maybe change it to like 6. But since it did not change the hydrogen bonding network, which was a very big adjustment that we had needed, we considered it unsuccessful. And so from this step, you would need to do a cast step, which is basically computational modification of your refinement results. And yeah, we had not really done that because we intend to do that. The resources are limited for that. So we kind of need to do that for the actual material that we are going to put in the research paper, which we are still waiting for from the synchrotron facility, because we had to send in the samples to get better quality or better resolution data. And then we will run through the whole process that I've just highlighted now with those results, and in hope of better peaks and also better structure solution. So to discuss a little bit or to conclude, PXRD is one of the ways you can use to get lattice information, lattice structure information, and there is very, very little way to do it without using compositional tools, and you would need to be able to use an integrated approach, so be able to maneuver between the two tools or between your many tools that you have at your disposal to actually find a suitable structure or a good solution structure. The predicted hydrogen bonding is good as a guide, but you still need to use your scientific or your chemical ingenuity to actually analyze what you get from your program as your scoring or your scores. As I had highlighted, this is very useful for pharmaceutical design, and yeah, you may maybe know someone who has synthesized something and they said, oh, but it's not soluble, or but it doesn't stay stable for a long time, maybe in in atmosphere or something. So in future, as I had mentioned, we are still awaiting data from a LISOS facility in Stanford, and we are going to run through the process and also extend this work to inclusion complexes. So I would like to acknowledge my supervisors and my team members in the supramolecular research chemistry group and the greater UCT. So thank you.
Thank you, Sicily. That was a very interesting talk. It occurred to me during the talk that it might be a candidate for electron diffraction. Have you thought of doing that?
Yes, so I didn't think about it originally, but I attended a conference, I think, at the beginning of the year. It was basically like light source school. So I did look at it and I did see that there were possibilities of doing it through that way. I'm still looking to apply to other light source facilities because we have more samples, especially in the inclusion complexes. So I did think about extending it to sort of like electron diffraction. So I'll look into it. I was thinking about it, but I haven't really started any applications towards that.
Yeah, you could actually take it to electron microscope unit and see whether you can see the microcrystals and get any
Yes, yes.
diffraction.
Yes, yes. Oh, I see what you're saying. Yes, yes. That's true.
Okay. Okay. Anybody have any questions for Sicily? We're on time now, or at least on our modified time schedule. So if there are no questions, I'm going to proceed. The next talk is from Oludari Ogunyeni from the University of Ibadan in Nigeria. Have you got your, yes, you've unshared now. And Olusani, Oludari, have you got your screen sharing capability?
I don't
It's
see.
Oludari Ogonyemi.
I do not see that name in the
So,
gallery here.
oh dear.
Yeah, I don't see that name in the gallery.
Okay. Okay, he was going to talk about steroidal pregnines in as 11B HSD1 modulators. Okay, and that's another drug design talk. Okay, it doesn't matter. I think what we'll do is we can have a 10-minute comfort break, and the next talk was scheduled at 12:50. Okay, and our time now is 12:42. So we can have 8 minutes and just relax. And then the next talk will be from Camelia Okudu from the University of Wyoming. She is there.
Yes.
Camelia, can you talk? Just to make sure that you can hear us.
Good morning, yes.
Okay. Okay, so you're going to be given screen sharing capability, so you can put your first slide up, and then we'll come back and start you on schedule at 12:50.
It's 4:50 or 12:50. Should I go ahead and start?
Okay, let me just say what your title is.
Okay.
We're going to hear Camelia Apudu from University of Wyoming talking about teaching biophysics using integrating generative AI, computational modeling, and physiological reasoning to enhance bioscience education. Sounds really interesting. Okay, I look forward to hear it. Go ahead, Camelia. Camelia? Your sound is not on.
Can you hear me now?
Yes.
Okay, I don't know what happened. Sorry. I was just saying before I begin, thank you for this opportunity, but I would like to collectively acknowledge that I am zooming from the ancestral traditional land of the Shoshone, the Arapaho, Crow, and the Cheyenne traditional First Nations, and we honor these First Nations people along with other Native tribes who call the Great Basin and Rocky Mountain region home. As the original stewards of this land, I acknowledge their enduring presence, their enduring connection to these lands, and I pay my respects to elders past and present. The motivation for my presentation is we want to better prepare future life science professionals for research environments that are increasingly data-driven and computational. Traditional biology teaching often stops at conceptual understanding, as our framework links these concepts with quantitative modeling and AI-supported reasoning. Generative AI serves as a scaffold for which we can teach the biological principles into quantitative forms. Physiological reasoning keeps learning grounded in real biological systems and clinical relevant contexts. Together, these elements build computational literacy, encouraging ethical use of AI and deepen understandings of biological mechanisms. In her article on AI in higher education, Dr. Tabitha Washington explains that AI is already deeply embedded in student life, workplace tools, and research workflows. She emphasizes that universities must intentionally align AI adaptation with academic values and develop institutional-wide strategies for its responsible use. A major challenge, however, is supporting faculty who have trained before digital research tools were common and may feel unprepared or skeptical. Providing practical frameworks and examples is essential to help these instructors see how AI can enhance, not replace, their expertise, and to ensure equitable access to AI-enabled learning environments. So our goal is to strengthen students' computational reasoning and data literacy by giving biology and biophysics learners, especially those with limited prior experience, accessible ways to engage with quantitative problem solving. By embedding computational methods with familiar physiological systems such as cardiovascular and oxygen transport processes, the work helps students see modeling not as an abstract skill, but as a meaningful tool for understanding real biological mechanisms. A key component is teaching students to use generative AI ethically and critically encourage them to question AI-produced outputs, verify assumptions, and integrate suggestions responsibly into their scientific reasoning. The instructional design is intentionally inclusive and accessible, using low barrier tools and culturally responsive practices to support diverse learners, including those across the diaspora, ultimately broadening participation in computational and biophysical science pathways. So we chose a physiological problem. I didn't adequately introduce my collaborator. I'm a plant physiologist and biochemist and a professor of botany at the University of Wyoming. And I collaborate with Dr. Semilia Okpodu-Puza, who's a biophysicist and animal physiologist, and she has a consulting company called the Gilded Alliance Group. We chose a physiological problem that can be applied to a broad number of eukaryotic systems, whether we're talking plant or animal. We selected the human physiology problem to demonstrate because there were open source data sets available on GitHub. However, we're planning to adapt this model to look at the change in bulk flow of water in the xylem in plants. So understanding oxygen saturation, particularly the shape and behavior of the oxygen hemoglobin dissociation curve, is conceptually difficult for many students because it involves multiple interactions and physiological variables, such as the partial pressure of oxygen, pH, temperature, CO2 concentration, and 2,3-phosphoglycerate concentration. So the students rarely see how these variables operate together. Most textbooks present this curve as static. So students see one classic curve, but never get to explore what makes it shift left or right. Oftentimes, learners struggle to visualize the nonlinear response. So small changes in physiology can produce large, non-intuitive changes in saturation. So real clinical scenarios are dynamic, but classroom examples are not. It's difficult to demonstrate hypoxia, anemia, fever, altitude, or impaired lung function without a dynamic tool or simulation. And as a result, students often memorize the curve rather than understand it. So one thing I want to point out with the oxyhemoglobin dissociation curve is, and I want you to remember this because we're going to use it later in the simulation that I'm going to show you, is the Bohr effect, which says that as the pH decreases, so if there's a decrease in pH, it's going to shift the curve to the right. If the pH increases, it's going to shift the curve to the left. And we also have the conditions for oxygen, CO2, and 2,3-BPG. So this model approach really enhances how students understand oxygen saturation. Instead of looking at a static oxygen dissociation curve, the model allows them to interact with it and actually manipulate the parameters. That helps them see the curve as a living dynamic system rather than a fixed image in a textbook. It also makes it very clear how small, subtle changes can produce dramatic shifts in saturation. When students can adjust variables like pH, temperature, or altitude, they immediately see the curve response, and that deepens their intuition for the underlying physiology. Another benefit is that it bridges computational modeling with real clinical interpretation. Students can make connections between what the model predicts and what clinicians observe in respiratory distress, anemia, or hypoxia. It also gives them the ability to directly compare normal physiological states with altered or pathological ones. They can toggle between conditions and quickly understand how these changes affect oxygen delivery. Overall, the activity promotes active learning. Students get to experiment, test ideas, and explore what-if scenarios, which strengthens both their conceptual understanding and their problem-solving skills. So we do not use the classic Hill reaction that most people use for oxygen dissociation. The reason why is because it describes only the equilibrium relationship between oxygen's partial pressure and hemoglobin saturation. In contrast, our activity for this module models the dynamics of oxygen transport. This requires solving several differential equations that describe diffusion and concentration changes over time. We use the finite difference methods, and therefore more appropriate because they allow students to simulate physiological processes directly rather than relying on the empirical steady state curve provided by the Hill equation. The Hill equation is empirical, not mechanistic. It's a curve fitting function and not derived from the laws of diffusion, not mechanistic with respect to blood flow or lung function. Thus, if the goal is to teach students mechanistic models like Fick's law, diffusions, and transport, it makes no sense to use the Hill equation. This model also, using the Fick's finite difference model also allows us to apply this to transport of nutrients in the xylem and phloem of plants. So each point in space, I, represents a location in the tissue, and each step in updates the oxygen concentration based on the diffusion coefficient. And this term in the equation helps us to see how oxygen flows into and out of a location. And so students can adjust these variables and run the simulation to understand oxygen saturation. So here's an actual workflow of how we use our model. So our first step is we start by introducing this overall concept. And the idea of training the next generation using a generative AI enhanced framework is a paper that Samelia and I wrote. And we have the students actually read this paper. And in the paper, we actually use BioPython in this paper. I'm now advocating for MATLAB, and I'll show you why. We use this, and we have GitHub data that we use, and we actually use that, and we explain to the student what oxygen saturation and dissociation curves and how it changed. After they review the paper that's in the Global Journal of Medical and Clinical Research Reports, they work up clinical scenarios. They either use the one that's in the paper, or they can actually introduce their own using Copilot. So they can actually use the Copilot and the MATLAB to help them generate a artificial data set. Or I would recommend that if students, oftentimes in physiology lab, we will actually have them take oximeters and measure their own oxygen saturation before and after exercise, and then we could create a data set that we could then further analyze. So in addition to using GitHub open source data, we also could generate our own. And at step 4, we use the MATLAB modulator. And then I explain why saturation and the dissociation curve can be challenging topics for students, especially when they try to connect the physiology to real clinical scenarios. And using the Copilot to generate clinical cases, we can talk about the ethics behind that. The AI creates realistic patient scenarios that can vary by pH, temperature, CO2 levels, altitude, and other variables. And this gives students authentic contexts to work within. And so we step through. This is the paper that we show them. Then I highly recommend, this is the teaching module that we've created at the math workshop that I went to in October of last year, that was held at Carleton University in Minneapolis, Minnesota. This module has learning goals, the MATLAB code, discussion questions with ethical questions incorporated for discussion, and a grading rubric. And I encourage anyone who's interested in teaching this subject, this would be a great workshop for you to go. And they often have scholarships to bring people in. It's really MathWorks was really worth it. And they have a whole resource that you can go to if you teaching computation with MATLAB. If you Google that, you should be able to bring that site up, and they're free to you to use. There's no fee. And I checked before I started this, and I saw that most universities in South Africa have access to MATLAB, that you have accounts, so you should be able to incorporate this into your teaching very easily. So I don't know if this will work, but we'll try. We can actually run the simulation. So when the students run the simulation, what I have done is I have actually allowed them to have the wrong information. So in this first example, what I did is I give them the code. This is in the paper. and I ask them to run the dissociation. And so they're able to run the dissociation constant, and they're able to get the information from dissociation over time. And then I ask the students to look to see what happens if the pH is shifted from 7.56 to 7.7. So remember, according to the Bohr's effect, if you raise the pH, you should see a shift of the curve to the left. And what I did was, in the code, I intentionally put an error in the code. And so one of the things when they run this, and I'm sorry the simulation is not running, so I can show you. It always worked when I was practicing. But anyway, you get a curve where this is not correct. And but then I asked the students to go and use their analysis to go through the code to see what the issue was. And what I found is, what they find is that I intentionally introduced an error so they would get the wrong shape of the curve. And that is to make sure they understood the effect of the Bohr of a change in pH. And so then when they correct the code, which is a minor change, they can actually use the Copilot. If they can't figure it out, one of the wonderful things about the Copilot is it will go step by step, line by line in your code to help you figure out where you made the error. And if this was running, you would see that I had asked them to add in this original code versus subtract. And so once they fix the code, they're able to get the right saturation curve. Whenever you raise the pH, according to the Bohr effect, it should cause the saturation curve to move to the left. And so they're able to then reinforce their understanding and simulate and run the simulate and evaluate the output, and not just accept what the AI gave them without critically evaluating it. So with this framework, generative AI functions as a cognitive support tool that deepens students' engagement with bioinformatics and data-driven reasoning. Instead of supplying final answers, the AI helps the students explore the biological questions, test assumptions, and generate scenarios that can examine through computation. This encourages active learning, as students must evaluate the accuracy and relevance of the AI-generated content and connect computational results to underlying biological processes. The approach also incorporates explicit ethical guidance, requiring learners to document how AI is used, justify analytical choices, and recognize issues such as transparency, data integrity, and potential bias. By normalizing responsible AI use within the coursework, the framework builds student confidence while maintaining rigorous expectations for analytical thinking and better preparing learners for modern research environments where AI augmented workflows are standard. The broader impact of this work is the ability to expand access to computational and biophysics education for diverse learners by lowering traditional barriers associated with programming heavy or mathematical intense coursework. By integrating AI support conceptualized modeling and physiological relevant examples, the framework is especially valuable for students across the diaspora and other groups historically underrepresented in STEM who may have limited exposure to computational tools. Emphasizing cardiovascular and physiological applications helps students recognize the societal and clinical relevance of computational biology, while the module design allows instructors to adapt approaches to different course levels, resources, and institutional settings. By centering ethical AI use and inclusive pedagogy, the project supports more equitable pathways into quantitative life science fields and aligns with broader efforts to diversify the scientific workforce. In conclusion, integrating generative AI, computational modeling, and physiological reasoning offers a powerful and scalable approach to enhancing biological science education. This project demonstrates that AI-supported workflows, when thoroughly designed, can deepen understanding rather than dilute rigor. The MATLAB-based oxygen saturation and modeling exercise illustrates how quantitative tools in realistic clinical contexts can be combined to strengthen both conceptual and practical learning outcomes. Looking forward, future work will explore expanding the framework to additional physiological systems and incorporating more advanced data sources, such as real patient data sets or wearable sensor data. There's also potential to formally assess learning gains related to computational confidence, ethical AI reasoning, and long-term student retention in biophysical disciplines. By continuing to refine and evaluate this approach, the project aims to contribute sustainable, inclusive models for training the next generation of biophysicists and computational biologists. Ultimately, this work underscores the value of interdisciplinary, student-centered pedagogy and preparing learners for the evolving landscape of biological research and innovation. Here's some of the references I referred to, and here's our contact information. And I'm open for any questions anyone.
There you go. Okay. Okay, Chart has raised his hand. Chart, will you ask your question?
Yes, thank you very much for a very nice talk. I really like this idea. It's a very nice hands-on approach. So I have two questions. Firstly, what coding experience do the students need to have in order to make use of this tool? And secondly, how do you ensure that the students still develop first principles understanding rather than over-relying on the AI-generated explanations?
So the first question, so you should know that as I went to this workshop, I have experience with R Studio, which a lot of people do, and BioPython. I had never coded in MATLAB. And so there is an on-ramp that all learners can take that MathWorks offers, and it teaches you fundamental principles in coding. So when I taught my class, I teach a computational class here at the University of Wyoming. I had different learners from all across my college, from engineering to agriculture. And so I had to make sure I onboarded all the students at the same level. The MATLAB is easier because they have an on-ramp, so you can check for their understanding of how to code. It actually is like train the trainer kind of thing. It teaches you as you go through. So you can also, and the other thing is this is not in isolation from you lecturing. You still have to lecture and give background. You still have the students still have to do the readings. This is why we start with the paper, because the paper talks about the physiology. You explain the various effects. What this allows is like a lab activity where they then can go in and manipulate and compare what they learn in the lecture from the textbook with their doing hands-on inquiry type basis analysis.
Yeah, very, very nice. Thank you very much.
Thank you, Camelia. That was. Any other questions for Camelia? I don't see any hands. Okay.
Yeah. Maybe just another quick question. Do the students also explore parameter uncertainty and variability in the parameters?
So no, I'm not a mathematician. I'm a biochemist, but yes, that could be. I can see how that could be integrated. I don't have that built in, but I don't see why it couldn't be integrated into the module.
Okay.
And that's the wonderful thing about those teaching tools that I shared with University of Carleton University in Minnesota. They allowed any one of those exercises, you can modify it to fit whatever you want. So if you want to take my exercise and modify it, you're welcome to do that. In fact, we encourage that. And we ask you, if you do it, then to upload it so others can see. So it's like a community of learners. It is taken into account that most of us were trained to I'm at the end of my career, rather my daughter's at the beginning of hers. So if you hadn't figured out, my collaborator is my oldest daughter. And so I'm seeing how to bring an old dog into a new trick. kind of thing. That workshop really helped me to build confidence so that I could now feel very certain, because I'd never used MATLAB. I'd always used BioPython or R.
It's excellent. Yeah, thanks a lot.
So those of us that are at the end of our careers are really learning from you. So I'm about to start teaching computational biologists.
Yeah, that's fascinating on all levels.
Okay, so we have to move on to the next talk. Lawrence, will you share the screen of Isaiah Igwe? Isaiah is from the Federal University of Dutsen-Ma, which was a geography lesson for me. It's in northern Nigeria, and he's going to talk to us about thermomechanical mapping of DNA under coupled salt temperature control with OxDNA2 coarse-grained simulations. Isaiah, would you go into full screen and carry on? Thank you.
Hi, can you hear me? Is my screen full?
Yes, your screen is full and we can hear you. Thank you.
All right, thank you. So my name is Isaiah, like I've been introduced. My name is Isaiah Igwe. I'll be presenting our work on thermomechanical mapping of DNA under coupled salt temperature control with oxygen DNA coarse-grained simulations. Actually, at fundamental level, this work is about understanding how microscopic interactions, particularly stocking and electrostatics, how we can translate them into macroscopic mechanical behavior of DNA. And more importantly, we want to see if this behavior can be described within a unified physical framework. Actually, DNA, as we all know, is a carrier of genetic information, but it's also it can also be treated as a mechanical polymer with fascinating mechanical properties. And when changes occur in these mechanical parameters, it can have a profound functional consequences in DNA. So, such as protein binding, chromatic organization, and likewise in nanostructure design. So currently, we have fairly good understanding of how temperature affects DNA. We also have a separate understanding of how ionic strength affects DNA. But these two variables are rarely treated together in a systematic way. So our work is to see how we can unify the effects of temperature and the effect of electrostatics on DNA. And that is exactly what this work aims to provide. That's how can we unify the effects of temperature and ionic strength. So to address this, we use the oxygen DNA2 coarse-grained model. We implemented it in LAMPS. LAMP is a large-scale atomic molecular massively parallel simulator. This will allow us to retain the essential physics. As you can see, this is the potential energy used in oxygen DNA. This will allow us to see the stocking, hydrogen bonding, the backbone flexibility, and at the same time, it will give us access to large scale, which other methods such as atomistic simulations struggle with. So crucially, we explored a full 3x9 parallel grid. So our work is not just a single condition study, but it's also a systematic mapping of thermodynamic space. So this is the snapshot, the structural snapshot results of our simulation. So this snapshot will help us to visualize the physics. As we can see, at low temperature, the structure is compact and well ordered. At higher temperature, we see that the structure also remains intact, but it appears more flexible and dynamic. So what this helps us to understand is that we observe, though there is a structural transition, but it's a gradual one, gradual fluctuation. So the softening, we see softening, but it didn't collapse, or it didn't get to the point of melting. That is denaturation. So we analyzed the structural stability of the DNA duplex. As we can see from this, even near 100 degrees centigrade, we do not observe any global denaturation. Instead, what we see is actually a localized flexibility, primarily at the end, as we, from that structure that is this. So this is important because it tells us that the mechanical changes we observe are not due to it's not due to catastrophic structural breakdown, but there is a subtle intrinsic change in the internal energy landscape. Again, another thing we observe here is that is actually an elasticity. The structure is getting softer, but not melting. Didn't get to denaturation of the structures of DNA. So here we examined the bending rigidity through the persistent length. As the temperature increases, we see that the persistent length decreases, and this indicates, like I've mentioned before, softening. But the key point is this: the decrease is stronger than the predicted, what is predicted by simple entropic models. So in simple entropic models, we expect a 1/T dependence, but what we observe deviates from that. And this suggests that the bending modulus itself is temperature dependent. So we also consider the torsional elasticity. Now, looking at the torsional stiffness, we see a similar trend. We see a similar trend, which is softening with temperature, but it is less pronounced than bending. And this suggests that bending and torsion are actually governed by different microscopic degrees of freedom. So in particular, bending appears more sensitive to stocking fluctuations, while torsion it tends to retain its structural constraint. So we are seeing a mode-dependent elasticity. So for axial stretching, sorry, this is supposed to be stretching. The heading is supposed to be stretching, and I think I didn't correct that. So for this is the stretching. Sorry. Okay. So the stretch, this is the axial stretching. The behavior is again consistent. We see the stretch modulus decreases gradually with temperature, here, but the response remains linear in the small Fox region, as we can see. So the helix still behaves like an elastic rod, even at elevated temperatures. However, we see that the slight curvature at higher forces suggests that the local soft regions are beginning to emerge. So this gives us like the subtle signature of internal heterogeneity. So we also considered the twist stretch coupling, and we see that the DNA exhibits the somewhat counterintuitive behavior of overwinding when stretched. So what we observe is that this coupling weakens as temperature. It weakens as temperature increases, and this is an indication that the geometric coherence of the double helix is being disrupted. So in other words, the helix seem to become more permissive to independent twist and stretch fluctuations. So this figure helps us to explain the deviation. So this tests the harmonic assumption underlying the torsional elasticity. So we see that at low temperature, everything behaves as expected. That's the Gaussian fluctuations, quadratic free energy. But at higher temperatures, we begin to see deviations. So the cortices increases, indicating a heavier tails, while skewness remains near zero, preserving symmetry. And importantly, the stiffness derived from fluctuations begins to diverge slightly from that obtained via the top. So the whole insight we get from here is that torsion remains mostly harmonic, but it begins to show signs of weak anharmonicity. So this shows that our Cosgrave model reveals physics that is difficult to capture in other simulation models. So actually, this is the central physical insight of our work. Here we see that when we plot elastic properties against stocking energy, the data collapses. So this tells us that stocking, not hydrogen bonding, is the dominant factor controlling DNA magnets. So hydrogen bonds maintain structural integrity, but in actual sense is stocking that controls the flexibility of DNA. So to formalize this, we introduced a dimensionless parameter. So as we can see here, chi represents the ratio of stocking energy to thermal energy. So this parameter actually captures the balance between stability and fluctuation. And importantly, it is independent of the specific control variable. So it is not temperature alone, and it is not ionic or salt alone. It is a combined effect. So that's what this model is showing us. So when we express all elastic constants in terms of chi, we have a collapsed onto a single curve across all sorts and temperature conditions. So this is also a strong, this gives us a strong evidence of universality. What appears to be complex multi-parameter behavior can also as well be reduced to a single underlying variable, which is the chi. So at all temperatures and at all sorts. Actually, I forgot to mention that we use the 3 different monovalent salts, that is at 0.5 monovalent salt, 1.0, and 1.5. Which is also the beauty of using DNA2 Cosgrave model. It gives allowance for this high monovalent salt. So we constructed a phase style diagram. Here we identify 3 regimes: a rigid regime, a thermally softened regime, and a pre-melting regime. So the transitions between these regimes are controlled by chi. So this essentially gives us a phase diagram of DNA elasticity. So this is the full framework of our simulation. So we see that both thermal fluctuations and electrostatic screening are both responsible for DNA stability. Here we see that electrostatic screening determines the baseline stiffness. Stocking interaction determine how that stiffness evolves with temperature. And of course, we have a unified description, which is the chi. So the full chain is electrostatics, stocking, scaling, then we have elasticity. So to conclude, we see that DNA elasticity is governed primarily by stocking thermodynamics, electrostatic interactions, which shift the baseline but do not control the scaling, and the entire behavior can be captured by a universal parameter. So this provides a unified statistical mechanical framework for DNA mechanics. Thank you very much for listening.
Thank you, Isaiah. Thank you very much. I'm calling for questions for Isaiah, please. Charles has raised his hand. Charles, speak.
Yes, thank you for an interesting talk. I was wondering about the upper limits of your salt concentration. So 1.5 molar salt is quite excessive. And then I would expect the electrostatic screening to be extreme. So is it possible that your model underestimates the residual electrostatic contributions to elasticity at this high salt concentration?
Well, I think from previous studies, we've seen that the Oxen DNA Cosgrave model can accommodate that. So the screening, the Debye-Huckel screening helps us to take care of that.
Oh, okay.
So actually 1.5 is a high is a high salt concentration, but I think previously the Oxen DNA is not able to capture up to that, but this is a modified Oxen DNA model. That's why you have 2 on it. So with this model, it gives us access to that high concentration, high salt concentration.
I see. Okay. Okay. Thank you very much.
Thank you, Isaiah. Camelia has a question. Camelia, do you want to ask a question?
Yes, very nice talk. I just wondered about, and do you know the sequence of your DNA? Because for plants, for example, if it has a large amount of GC content, it's going
Yes.
to fold differently, and the amount of salt that it's going to affect it. So I'm just curious, are these simulated strands, or this is real synthesized DNA? And if so, if it's
Yes. So
simulated,
this
can you
is
run the model with high GC content?
yes, thank you very much. So this is a simulated, not synthesized in the lab. It's purely a computational work. So we use the 500 long strain. It's 500 base pairs duplex, and we have the sequence is 50%, 50% GC.
Thank you.
Thank you. Thanks, Isaiah. Are there any further questions for Isaiah? Please indicate and speak. Okay. I think we have a few minutes before the scheduled time of Emmanuel Ng's talk. Perhaps you can have a break for a few minutes and then get back to Emmanuel's talk on schedule at 13:40, 4 minutes time. You happy with that, Emmanuel?
Yes, I'm very happy with that. Thank you.
Okay, and then Lawrence, please will you share Emmanuel's screen, or at least allow him to share his screen and stop sharing Isaiah. Thank you. Okay. If everybody's ready, we can proceed with Emmanuel's talk, Emmanuel Ng from Biostruct Africa. And he's going to talk to us about the structural basis of specific lysine transport by Pseudomonas aeruginosa permease lyse P. This is this work that you've done in Diamond, Emmanuel?
Partly diamond, and I also did some cryo-EM work in Sweden.
Okay. Okay, very interesting. Okay, thank you very much. Let's go ahead.
Yeah, thanks, Trevor, for the introduction. So the title of my talk is Structural Basis of Lysine-Specific Transport by Pseudomonas aeruginosa, lysine permease, LysP. And this work is based on a recent publication in Nature Communication. So my talk is going to be focused on this core aspect. So I'm going to give an introduction, the stability and biochemical characterization of LysP, functional characterization, looking into the structure and binding side of the protein, and then the molecular basis of lysine selectivity by LysP, and then looking into the LysP, lysine, and nanobody interaction, and then the proposed mechanism. So just to introduce myself, I'm a structural biologist. My research focused on structural determination of drug target, functional characterization of these drug targets. I'm also involved in research training and workforce development for Africa-based researchers, which I co-founded BioStruct Africa, and I am the CEO currently running this organization. And then I'm also involved in antibiotic resistant research to inform health policy on antimicrobial resistance. The introduction. So the protein I'm going to talk about, it's a membrane protein, as you see here, called LysP. So it's specifically transport lysine from the outer membrane to the inner cell, from the outer cell to the inner cell. So what does LysP do? So it's specifically transport lysine. Unlike the other amino acid transporters, they are very promiscuous, which means they can transport a broad range of amino acid, but LysP is very, very specific. And this is because when the bacteria, so LysP is mostly found in the enteric bacteria that are exposed to very extreme acidic condition, as in the mammalian stomach. So once the bacteria recognizes this acidic stress condition, the LysP interacts with Cat-C, and Cat-C upregulates Cat-BA operon. And this operon leads to the production of Cat-A protein, and this Cat-A decarboxylates lysine that has been transported by lysine using a protein which couples a proton as well into cadaverine, and there is a CO2 release. So this cadaverine is transported to the outer membrane by Cat-B. So in essence, the decarboxylation of lysine consumes a proton here. So the constant removal of proton helps to neutralize the acidic environment. So LysP, in essence, has a transporter function and a regulatory function. And it shares high sequence similarities with other enteric bacteria, as you can see here on the list, Vibrio cholerae, Salmonella typhi. So these organisms share a similar mechanism of lysine-specific transport. So several years of trying to get a structure of this protein was unsuccessful because the protein was very, very unstable. So what we did was to purify the protein, as you can see here, and inject the protein into llamas to generate antibodies, which in this case we call nanobodies, which is a fusion protein partner that helps to bind to the protein and locks it in one conformation and helps to stabilize it. And it's evident here, as you can see, the melting temperature of LISP in comparison with LISP nanobody complex. You can see that there is 20 degrees increase, which is huge in the structural biology sense. And if you see here, you can see a peak shift where you have LISP alone and in the complex. So there is clearly a complex form. And also on SDS page, you can see once you run the complex, this peak. You can see here you have two protein, and this is the free nanobody here. You can see. So the protein, the LISP protein that was injected, if you do circular dichroism spectroscopy, you can see that it's predominantly alpha helix. So the functional characterization of LISP. So LISP specifically transport lysine. It doesn't transport the other amino acids. So we use artificial membrane, as you can see here, where we reconstitute LISP into this artificial membrane and then measure the uptake of radioactive lysine. This red is no LISP, that's the control, and you can see there's a robust uptake of the radioactive lysine. And also we did the IC50 of lysine and arginine. You can see it's very specific for lysine. Also, we try to compete with cold amino acid, 10 millimolar. None of these could inhibit the transport of lysine except for an analog of lysine, which is L4-thiolysine. So binding studies also show that it's very, very specific for lysine and also thiolysine. For arginine, there was no binding seen in this concentration range. We also showed that the protein transport lysine utilizing a proton gradient. If you have a gradient of pH 7 inside and 4 outside of this artificial membrane, you can see there's robust transport. But if you have pH 4 inside and outside, there is no transport. If you do sodium chloride, you can see that it doesn't use sodium, because it doesn't use sodium gradient. The structure, so we solve the structure of LISP, L-lysine, and the nanobody in an inward occluded state. So this was done by cryo-EM. So the next speaker, Rebecca, is going to tell you more about cryo-EM. So these are the particles obtained, and we did the 2D classification. You can already see here in the 2D classification, the nanobody is pointing out, and this is the core that has the lysine transporter. So based on that, we solve the structure, and you can see lysine is trapped inside, and the nanobody is located on the periplasmic side of the cell. And the protein has 12 transmembrane segments. So if you overlay the alpha fold, which is in gray, and this structure, which is in green, you will see that there is movement of these helices here, which is helices 1A and 6B. So which means the protein is already open into the cytosol, ready to release the substrate. So then the binding site. So the lysine makes contact mostly with polar uncharged amino acid residues. That's the amine group of the lysine. You can see here serine and asparagine. And it forms a cationic pi interaction between tryptophan 105 and the amine group of lysine. So it also forms some hydrogen bonding with glutamine 1,1,2. So as you see here, so there is a phenylalanine 215 and a tryptophan 105 that sandwich the amine group of the lysine as shown there. So we did mutagenesis to mutate all these residues and perform the transport assay to see if this is going to diminish the function. As you can see clearly, it does. And all the mutants, when mutated, we purified and showed that they're still monodispersed, or rather still homogeneous and not in the void volume. So there is a lysine 162 of lysP that is highly conserved in all cationic amino acid transporters. And we propose that this lysine is the one responsible for proton coupling, although more experiments needs to be done here to validate this. So why does this amino acid transporter specifically transport only lysine, while the other amino acid transport a broad range of amino acid? So we perform sequence alignment of the Pseudomonas aeruginosa lysP and the other orthologs, including a cationic amino acid transporter. So the cationic amino acid transporter here is from a bacteria, this one in red, and the structure has been solved with arginine. So if you perform sequence alignment, you realize that the tryptophan I told you about, that forms a cationic pi interaction with the amine group of lysine, is highly conserved. But for this amino acid, cationic amino acid transporter that transports arginine, you have a tyrosine instead of a tryptophan. And we also do structural alignment of the Pseudomonas lysP, the cationic amino acid transporter, and also the E. coli arginine transporter. As you can see here, the tyrosine is highly conserved, but the tryptophan, which is only in lysP, in the other two proteins that transport arginine, you have tyrosine. And this is because the side chain of arginine is very bulky, and the tryptophan doesn't accommodate the arginine group, but rather it can accommodate the amine group of lysine because it's much more smaller. So as you can see here, it's the tryptophan extends right to this region. So this is how the protein has been able to specifically recognize lysine and not arginine. And I'm using arginine here as a reference because they are the closest in terms of cationic amino acid transporter, in terms of cationic amino acid, rather. So you also have these other residues here that are also very important for the recognition. And the amine group of lysine with the tryptophan is 4.6 angstrom away. So this is the lysP L-lysine nanobody interaction. So this is the nanobody in the periplasm. This is the lysP, and this is the region where you have the interaction. So you can see here, we've zoomed out and you can see more clearly the residues that are involved. You can see hydrogen bonding here between the nanobody, asparagine 76 and serine 276, and so on. You can see the CDR regions is penetrating deep into the transporter, which is not, I'm not surprised why it stabilized the transporter by 20 degrees Celsius. So the proposed mechanism, so LISP specifically shuttles L-lysine from one part of the membrane, that's from the outside to this cytoplasmic side of the cell into the cytoplasm. So it utilizes mainly these two helices, 1 and 6. So helix 1 and 6, they are some sort of broken helix. So you can see here it's broken in the middle. And once the transporter recognizes the lysine, you can see here this 1B and 6A is open. And once it binds, then this closes. So once this closes, 6B and 1A opens. As you can see here in the inward open. And then it releases the amino acid into the cytosol. So I just want to highlight some of the other things we're doing on the continent. So we've been doing training in AlphaFold and other experimental structural biology techniques. So we ran a pilot workshop on AlphaFold in Cameroon in 2024, where we trained 20 people, and based on the success, we've been able to scale up that training to reach out to 100 scientists on the continent. And this is the highlight of the workshop. 100 people trained, and we introduced the train the trainer model, where trainees who were in the previous workshop comes to this other workshop and then act as facilitators with the guidance of a senior scientist. So that was very, very successful. And then we now have started hands-on training in recombinant protein purification, which is something that I think the continent really needs. I've been to a lot of institutions and institutes. I realized this skill is not available there. So we've started this. So we, in partnership with Carvey Institute of Clinical Research at the University of Nairobi, we are running a pilot workshop to train 10 people in recombinant protein production. And based on the success of that, then we can scale up to reach out to more people on the continent. And then we're actively establishing platforms that can bridge the gap between genomic research and structure-based discovery research, because there's been a lot of money into genomic research, but very little amount of money has been invested in structure-based drug discovery research. So we're trying to establish platform to bridge that gap, and in partnership with global collaborators, we should be able to do it such that we're not like a standalone facility, but bringing in partners that can help bridge this gap. So that brings me to the end of my presentation. I want to acknowledge the Wellcome Trust for funding this research, Swedish Research Council, and SciLife Lab in Uppsala. Thanks.
Thank you. Okay. Thank you very much, Emmanuel. That was a beautiful talk, beautifully presented, beautifully organized. and absolutely superb in every respect. I'm going to ask you a few questions about it, but I want to actually comment on. I really think that your contribution to structural biology in Africa through the training in AlphaFold has been spectacular. And I think it's been a wonderful tool for introducing people in Africa to structural biology. And I think you've absolutely hit the nail on the head with the need to recombinantly express proteins. I think also that is a remarkably useful activity to initiate. Now, should we go on and talk about the lysine transporter? With respect to the lysine transporter, did you model the difference between putting the tyrosine and the tryptophan in the position that you showed, and to see that it actually did discriminate?
So I think the closest was we mutated that residue into tyrosine and then measured transport assay to see if it's going to transport lysine. But there was a little bit of transport, but it was not as robust as when you have a tryptophan. So it did not kill the transport completely, but there was a reasonable, decent amount of transport. So it means somehow it's if you have tyrosine, it can make the protein become promiscuous again. But this is also very complex because there are also other residues that are involved, like the polar uncharged amino acid, asparagine and serine, that forms like really close, very strong hydrogen bonding with the amine group of lysine during the transport cycle.
Okay, that's fair enough. Camelia, do you want to ask a question? Go ahead.
Yes, very quickly. Excellent talk. I was just wondering, do you think the lysine transport could be targeted as a way of controlling the bacteria infection?
Well, that is the next stage of our research. So very good question. That's the next stage. So we want to, because they've just described how this mechanism is in terms of acid resistance, but we don't know if you delete this protein, what can happen. So we want to investigate that. And also in Pseudomonas, it could as well, because there are some researchers describing it as like contributing to virulence. So this is also another angle where we can target LysP as a virulence factor in most cases where in case of antibiotic resistance, this could be an important approach to target virulence factors. So yeah.
Okay. Any further questions for Emmanuel? Okay,
Okay, thanks for listening.
Okay, thank you very much, Emmanuel. Please unshare your screen. Rebecca is here now, and she can be made a co-host so she can screen. Thank you very much, Emmanuel. Hi, Rebecca. We know that our next speaker is Rebecca Thompson. She's working for Thermo Fisher Scientific, who are the manufacturers of cryo-electron microscopes, one of the two manufacturers in the world. But she has an excellent talk in which she introduces people to the principles of cryo-electron microscopy and the usefulness of cryo-electron microscopy that we've just heard about from Emmanuel. So Over to you, Rebecca.
Thanks, Trevor, for that lovely introduction, and I hope I can do it justice. And just to say thank you so much for the invitation to be with you all here today. I had the great pleasure of being in South Africa just a few weeks ago now, and really saw what a vibrant structural biology community, and more widely a protein science community was building there. So it's a great pleasure to have the opportunity to speak with you today about a technique which I think is possibly one of the most exciting techniques in the landscape at the moment. So as Trevor said, I currently work for Thermo Fisher, who manufacture cryo-electron microscopes. I joined 3 years ago now, and prior to that, I was running a cryo-electron microscopy core facility at the University of Leeds. So have lots of experience hands-on with these instruments and also working up projects. So if after today you'd love to chat further about your project, I would like nothing more. So my contact details will be at the end, and I'd love to speak with you more about your projects and what you're hoping to achieve. So today I'm hoping to run through a little bit around cryo-electron microscopy. What is it, and why is it useful, and how do you get started? So obviously, cryo-electron microscopy sits within a spectrum of a whole variety of different structural techniques. And hopefully, as I'll show you as we go through, the cryo-electron microscopy allows us to tackle certain types of specimens, certain types of protein, and get certain types of information, which simply isn't possible through any other technique. And one of the reasons that I really fell in love with electron microscopy was how flexible it is as a technique. So whether you're interested in individual proteins, macromolecules, cells, or tissues, there is an electron microscopy technique which can be used to help examine your specimen. So today we're really going to be focusing in on cryo-electron microscopy, so our ability to generate high resolution structures. And I wanted to, I guess, kick off and allude to the fact that there are two primary techniques by which you can use cryo-electron microscopy to solve structures of proteins, so to generate high resolution structural information of proteins. And today I'm going to be focusing on the technique on the left, onto single particle analysis. And we'll go into this technique in more detail as we go through. But I wanted to say from the get-go that there's a whole other set of techniques or within electron microscopy, cryo-electron tomography, which are especially suited also to be looking at cells and tissues and proteins within these cell and tissue environments. And I'm not going to have time today to touch on any of these, but again, if you're interested afterwards, I'd love to have a chat further. So cryo-electron microscopy is not a new technique. It's been around for many, many, many decades. But really, in the last, I would say 20 years, but particularly 15 years, we've had an enormous revolution in terms of the technology and the software that's available. And what's been really exciting is to see how this technology is being used. And in fact, the development of the technology itself was awarded the Nobel Prize in chemistry back in 2017 now. And then recently, two subsequent Nobel Prizes have been supported by the kinds of data, the kinds of structures which you can bring out of a cryo-electron microscope. And of course, there's lots of different ways of solving structures, and I'm sure you're all very aware of X-ray crystallography and NMR as other structure determination techniques. And historically, X-ray crystallography has really led the way in terms of the number of researchers globally solving structures. So this graph basically shows the number of structures. It's on a logarithmic scale. So it shows the number of structures solved by the top one, X-ray crystallography, and then in this sharply rising yellow line here, we have cryo-electron microscopy. So we're expecting in the next couple of years that cryo-electron microscopy will probably become the most widely used technique for solving protein structures experimentally. And we'll go into the reasons why in the next couple of slides. So we've seen a huge growth in the adoption of cryo-electron microscopy and the types and diversity of structures that are being solved. So this graph on the left shows the number of entries that have been deposited into the electron microscopy data bank. And we can see again that line is on a very steep trajectory. So of course there are more people adopting this technique. But I think actually what's most exciting is the quality of the data that we can now routinely get out of these microscopes. So the graph on the right shows entries into the electron microscopy data bank by year, but also by resolution shells. So the structures in this purple section here are low resolution, and what you might, some of you may have heard the term blobology before, and this is something which people used to say often to electron microscopists, certainly if you go back 15 years or more. Why would you bother using this as a structural determination technique? All we can get is very, very low resolution information, blobs really, of what our proteins and macromolecules look like. And of course, fast forward to today, actually nearly a third of structures being solved by cryo electron microscopy that are deposited are better than 3 angstroms in resolution. So of course at this resolution we can really be identifying, we can be building protein structures de novo, we can be examining small molecule binding, we can be getting a whole host of structural information. And in fact, I like showing this example because this was the top left, this blobby structure was the first ever cryo electron microscopy structure that I solved back in 2010-ish. And then we saved these grids and put them into a microscope back in about 2020 now. And we just put the same grids into a modern microscope, and a structure just popped out at, I think the global resolution was about 4.5 angstroms, because this is quite a heterogeneous complex. So really amazing what a difference these modern instruments can make to the quality of data that we can get out. So why cryo electron microscopy? Why has the usage of this technique really exploded? And I think I can sum it up by saying, as scientists, we're interested in solving the structures of our proteins, of our macromolecules of interest, in as close to their native environment as possible. And often the biology which we're studying is flexible, it's heterogeneous. That might be in terms of compositional heterogeneity, maybe the complex has got different binders in different states. Maybe there's conformational heterogeneity. Pretty much every protein complex we work with has intrinsic dynamic properties, and it's these dynamic properties which really allow us to understand how the molecule is working. But of course, in techniques such as X-ray crystallography, we have to generate a very, very pure sample and get this into a crystal form before we can solve a structure. And this would typically involve using non-physiological pH and salt conditions. In cryo electron microscopy, if we can recombinantly produce your protein, or if we can produce a protein sample, then we can handle a large amount of, not continuous, but we can handle a large amount of heterogeneity in that sample. We can work with samples which might have different factors bound, post-translational modifications, all of this complexity, which is actually interesting from a biological question perspective. We can actually examine this and study this using cryo electron microscopy. And the other great news from a protein purification perspective is that we do also need much less protein in terms of volume and concentration. So there's really been a huge growth in the number of researchers using cryo-EM, and this was a study recently looking at how structures are being used in the design of new therapeutics. And here you can see that cryo electron microscopy structures are being used to tackle a wide range of diseases. And I always like to show this example. So there is now a vaccine available against RSV virus. And I like to show this example because I personally benefited from this vaccine just over a year ago now. And I think it's incredible how the structures that are being solved are used to generate impact in the clinic in such a tight turnaround. So having these high quality structures available is really helping to accelerate that medicine's discovery process. So before I go into kind of how to get started in cryo-EM, I wanted to share a case study that I really like, because I think it illustrates a lot of where electron microscopy has come and what is possible now to do with this technique. So there is a protein complex, CDK7, which is in eukaryotic cells, a master regulator of cell growth and division. And of course, if we're saying cell growth and division, what I will say next won't surprise you. This is obviously, this is often dysregulated in a number of different cancers. So has been a target of interest to the pharmaceutical industry for some time. However, despite a lot of attention on this complex, there have been huge challenges tackling this complex from a drug discovery perspective. There have been clinical trials that have been abandoned, and a big reason for this is there are a large number of structural homologs. So getting selectivity with these small molecules is really crucial. Despite a huge effort in this space, no X-ray crystallography structures were available of this complex. So this complex is small-ish, it's 85 kilodaltons, and it doesn't have any symmetry. So a group in London, Basil Grieber's group, were interested to see whether they could use cryo-electron microscopy in a small molecule screen against this complex. So the short answer is yes. They were able to take this protein, prepare cryo-electron microscopy grids, and I'll talk to you about the practicality of that in the next section. And using a dedicated cryo-electron microscope, in this case the Glacios 2, they were able to collect on each of these samples, each of these grids, a very small amount of data. So this was about 1 hour of automated data acquisition. And they were able to use this to solve structures to a resolution which was between 3.5 and 4.5 angstroms. So not particularly impressive resolution, but certainly sufficient to see in purple here where these small molecules were binding. And of course, they were then able to take these samples further and collect more data. And with 4 hours, we see the resolution improves. You start to be able to say something about the pose of the inhibitor. And of course, we can then collect more data still and get a higher resolution structure. So in just short of a day's worth of data, this particular complex went to 2.3 angstroms. So again, at this resolution, we can really be building in our protein structure de novo and get very accurate information about how these small molecules are binding. So in this study, they were able to use cryo-electron microscopy to solve not just one structure of this very challenging protein, but to solve a host. In this case, I think it was 24 structures with different small molecules bound. And then use that information to be able to then put forwards into the medicine's discovery process. And the reason that I really like this story is because this protein is not easy. It's not an easy target in any way, shape, or form. And by other techniques, this project was not tractable. But using cryo-electron microscopy, they were able to generate these beautiful structures and make this a meaningful target for the next stage of conversations. So microscope hardware is obviously important in order to be able to generate high resolution, high quality data. But actually the type of work that I've just shown you is really driven through also the advances of the software that's on these machines. And we now on, for example, the Glacios or the Cryos electron microscopes from Thermo Fisher offer a software called EPU. Latin for e pluribus unum, or out of many one. So the idea is out of many individual particles, we get one structure, and I'll talk about that a little bit later. But we can use this to mean that on a Glacios or a Cryos microscope, we can load 12 samples at a time, and in a completely automated manner, we can be going in and collecting data on each of those grids. So not only has the technology, the hardware really evolved, but the software is also allowing us to solve structures of more and even trickier proteins than previously. So hopefully I've convinced you that cryo-electron microscopy is a cool structure determination technique, if you excuse the pun. And I think that it's it's a fantastic technique, whether you're studying anything from a small enzyme complex through to a large heterogeneous pleomorphic virus, kind of anything in between. There are techniques which will allow you to study protein structure there. So in the final 10 minutes of the talk, what I wanted to just do is give you a little bit of a practical, okay, well, what does this look like? So for this section of the talk, I'm going to pretend that you have been able to express and purify your proteins. You've probably gone through a process of recombinant expression, and you've purified your protein so that you have now a nice purified protein complex with a nice, hopefully single-ish peak down your size exclusion. So you now have this protein. What's next? Well, the first thing that we need to do is get this onto a sample carrier to get it into the microscope. And for this, we buy cryo-electron microscopy grids. These grids are commercially available, and they have different properties in terms of the hole sizes, for example. But to be honest, the one that's shown on the screen here is the one that basically everybody starts off with. So you take this little sample carrier, this grid, which is shown just on the bottom here. And these grids are 3 millimeters in diameter, metal discs. And out of the box, they're quite hydrophobic. So the first thing that we need to do is render these hydrophilic so that we can apply our film. And you can get special devices to generate a glow discharge or a plasma to render the surface hydrophilic. But you can also just put it under a UV lamp simply, and that works pretty well as well. Okay, so we've got our sample, and the next thing we need to do is put the cryo into cryo-electron microscopy. So we're interested in studying our proteins in as native-like condition in the electron microscope as possible. So the inside of the electron microscope is kind of not dissimilar to the environment that you would find in space. There's a vacuum, and we have high-energy radiation, high-energy electrons coming down the column. And we're interested in looking at our protein, our living, our organism, our cell. We're interested in looking at this in this very hostile environment. So we can use cryo-electron microscopy to preserve our sample and allow us to be able to look at it in a native-like condition inside the electron microscope. So when we talk about freezing our samples, I always like to talk through this example with an apple. So if you took an apple and you put it into a freezer, you let it freeze, and then you took it back out again, and I said, would you like to eat this apple? Then you're going to say, absolutely not. A, why are you offering me an apple? But B, this apple is now mushy, it's gross, I don't want to eat it. And the reason it's gone mushy is because that apple froze slowly. So all of the water within that apple turned from liquid water into solid water, into ice. And those ice crystals have ripped through the tissue structure of the apple, meaning when it thaws, it gets all mushy and not well preserved. So when it comes to cryo-electron microscopy, when we're freezing our protein samples, we need to be freezing these to cryogenic temperatures. And the trick is to do this very, very quickly. If we freeze our sample quickly, we can trap it in a state which is, if we freeze it very quickly, we can, rather than giving the water molecules time to rearrange into solid ice crystals and disrupt our sample, we capture that water in a disordered state. So the water is in a disordered state, and the solid that's formed is amorphous ice, effectively. So we have our sample trapped in a layer of what's called vitreous or glassy ice. So we need to freeze our sample to cryogenic temperatures very quickly. And the invention of this technique was what Jacques Dubochet was awarded the Nobel Prize for back in 2017 now. And in this technique, he showed that you can freeze, this is a picture from his Nobel lecture, you can freeze samples into liquid ethane, which is cooled by liquid nitrogen. So liquid ethane allows us to freeze this sample very, very rapidly, much more quickly than if we froze it into liquid nitrogen. And this means that we can trap our sample in this vitreous state. So what does this look like in practice? So this is a very fast video, I'll just show you, but basically we take a pair of tweezers with our electron microscopy grid on. We apply 3 microliters of sample through the port in the side of this instrument, which is called the Vitrobot. A pair of blotting arms then blot away most of that liquid to leave a thin film of tens of nanometers. And then that's then plunged into the liquid ethane cooled by liquid nitrogen. So the grid is then transferred to the liquid nitrogen, and that grid can then be stored under liquid nitrogen until we're ready to image in the electron microscope. And you can freeze a whole variety of different samples in this way, as I've mentioned previously. So it's a really very, very flexible sample preparation technique. So what ideally we want is our sample in lots of well-distributed and in a good series of angular orientations. Unfortunately, often this doesn't happen, so we can have some problems at this stage with our sample not spreading into a nice even layer on the grid. And there are lots and lots of variables that can impact this. So sample preparation is a very big topic within cryo-electron microscopy, and I wanted to highlight to everyone that actually there's going to be in just a couple of weeks now a mini series hosted by the Royal Microscopical Society. So this is an online meeting, it's free to sign up to, and it's going to be starting off with a session on sample preparation, and then there will be data collection and image processing as well. So they'll be going into much more detail on everything that I'm talking about today. So once we've got our grid and we're ready to put it into an electron microscope, these are the electron microscopes which Thermo Fisher offer. The Glacios and the Cryos both have these autoloader systems which allow 12 grids to be loaded into the system at once. So these are much higher throughput. Apologies. Sorry about that. So once we get that sample into the microscope, we're relying on, well, we basically have a series of software available to us. And when I first started in cryo-electron microscopy decades ago, or 15 years ago, more than that now, I don't know, anyway, a while ago, the whole process was completely manual. So we would put it in, we would be manually moving to different areas of the grid and having to make a manual assessment, which when you've been doing it for a long time is very, very possible. But when you are first starting out, it can be quite tricky to understand what looks good and what doesn't look good. We're really fortunate these days that there is a whole variety of software available to help support this screening process. And also, for example, AI, I know this is a very, very big theme. We can use existing data sets to train this software to be able to, again, make automated decisions. So I'm going to skip through these on the software. And like I say, if you were interested in finding out more about the software, there'll be one of those webinars in a couple of weeks' time. But basically, when it comes to cryo-electron microscopy, the data acquisition in the middle is kind of the easy bit. So your sample preparation, your protein production, getting that onto a grid and having that optimized can be a process that certainly requires some thought and some project design and can take some iteration to get that process right. Once your grid is looking good, if you're on a Glacios instrument, for example, then or a Titan Cryos instrument, then the actual data acquisition, this should be the easy bit because the instruments in terms of the hardware and the software have really come so far. But of course, out of the microscope, we then get our raw data, our micrographs, and we then need to process these from a 2-dimensional image into our high-resolution 3-dimensional reconstruction. So again, I don't want to run over, so I'm not going to go into this in any detail other than to say what effectively we get is a micrograph, which has, you can consider it an almost projection of our macromolecule of interest. We can then use software to pick out these individual molecules, which are essentially our protein, then all at different angles. So you can use software to classify those, to group those together. And then if you can then calculate the angular relationship between each of those two-dimensional projections, you can then use that to regenerate a high-resolution 3-dimensional projection. And again, the software, in order to allow you to do this, has come an awful long way. CryoSpark is now the most popular program used by the community, and it's free to access for academic communities. And yeah, if you want more details on image processing, I'd be more than happy to chat. And like I say, there is that webinar in a few weeks' time. So I just wanted to finish off by saying there have been really huge advances in cryo-electron microscopy in terms of the resolution, the quality of the data that we can get out, and also the throughput and the numbers of structures. And if you have access to these instruments, then this can now be considered really for many categories of protein. If you can make it and you can get it onto a grid, then the process can be pretty routine from there in. So we've had over a decade now since this revolution in resolution in cryo-electron microscopy. And I think that where we are today is incredibly exciting because more and more challenging samples, heterogeneous complexes, biologically relevant samples are now being examined using cryo-electron microscopy. And the next frontier, which I mentioned right at the beginning, is I think we now have a potential as structural biologists to now look at these structures not only in their isolated protein form, but put those structures back into their native cellular environment and really understand how they're functioning there. And I think this is a very exciting next frontier for protein science. So on my last slide, for anybody who is interested in getting started, like I said, I'd be more than happy to chat one-to-one about your project, because there are many centres which are available which accept applications from anyone in the world to be able to potentially go and access equipment at their sites. So like I said, I'd be very happy to signpost for anyone who is interested. And with that, I'll finish. My email is here. I would love to chat to any of you further. And again, I've just put this QR code up, which is for the Royal Microscopy Society hosted Introduction to Cryo-EM mini-series, where they'll be able to go into a bit more detail than I've had time to do today. Okay, and that's all I've got, and I'd love to take any questions.
Thank you very much, Rebecca. It was a really exciting talk, and I hope that people will respond to it. So what are the questions for Rebecca, please? Come on, guys.
I had actually, so let me raise my hand. Trevor, I have a couple questions.
Go ahead, Lawrence.
So I have one question I've always been afraid to ask, but I will ask it now. Where did you get the liquid ethane?
Well, so liquid ethane, you can get it from, basically, you can put it into just, it comes in a gas cylinder, basically. So you put a 2-stage regulator on it and then make sure that you have a relatively low pressure coming out. So you just put like a pipe on the end of it. But we've actually, I'm not going to lie, there are a couple of places in the world right now that have an ethane supply chain issue. So you can just take methane camping gas, and propane camping gas, and do this in a similar way. So we've got, I can share this. So if anyone has, yes, although I've shown you can use a Vitrobot here, there are lots of people all around the world that use manual plunging devices, and there are lots of designs for these which are shared online. Again, I can share the papers for those. And yeah, propane actually works really well as well. So again, you can just take like a camping gas cylinder, stick a regulator on it, and then liquefy that inside the liquid ethane. Obviously, we're working with relatively low volumes. In some countries, it's recommended to do this inside
you've frozen, Rebecca.
A chemical fume hood. But actually, in many countries, so the UK, for example, because it's a low volume and it's a low flow, then people just do this out on the bench.
I believe that in the early days, propane was actually considered to be better, but the problem with the propane was that it's generally dirty.
Yeah, exactly.
And that was what made it unsuccessful as a tool in electron microscopy, whereas the ethane that was available was sort of medical grade and much cleaner.
Yeah. So I have some images that I can share. We had a couple of groups recently that we've been talking to on this because they've been struggling to get hold of the ethane, and the grids look beautiful and very, very clean. So you're exactly right, Trevor, that it can be more contaminated, but if access is an issue, it can be something to explore.
Have another couple of questions?
Yeah, please.
There's time, Trevor.
Go ahead.
Do you think that a ethane jet can be used in like a serial femtosecond crystallography context to combat the sort of destroy before diffract problem?
Yeah.
And is there going to be a time resolved cryo-EM in the near horizon?
Yeah, absolutely. So this is a brilliant question. So I'll take the two separately. Liquid ethane jets, yes, and these are already available. So there are two companies. There's one called Vitrajet, and one called EasyGrid. Again, I can send you the papers for both of them. Which sample preparation devices which use liquid ethane jets instead of plunging into liquid ethane to freeze your grids. The advantages over this are mostly, so EasyGrid, for example, is really set up for freezing cells on grids. Because of the jet vitrification, you get an even faster freezing rate. So you can freeze thicker samples, for example, whole cells. When it comes to time-resolved electron microscopy, you can actually achieve low millisecond freezing by plunging with the right devices. So again, this is a really exciting area of study, and there's already some groups globally working on these time-resolved devices. By using, for example, a microfluidic chip so that you can mix together your enzyme and the substrate or whatever it might be. You can get rapid mixing and then freezing on the grid, again in kind of the low millisecond time frames, which is very exciting. And there's even one group in Switzerland which are using lasers to, once you've already vitrified your grid, use a laser to in almost like a femtosecond, like very, very quick timescale. So if the process you're looking at is happening on a very, very quick timescale, you can use that kind of approach, which is still very experimental, I think. But yeah, no, time resolved electron microscopy, definitely an exciting area, and I think it really comes down to project design. So thinking about what timescale the biological phenomenon is happening on and how that can be triggered. Yeah, like I say, there's some exciting work, so I'd be very happy to send you some papers on that and chat further if you're interested.
As much as I'd love to continue the conversation, we are running out of time, and we have another speaker or two speakers waiting. So we're 6 minutes over time. So I'd like to thank Rebecca very much, and would everybody give her a round of applause? Thank you. Thank you very much for presenting to us.
Thank you so much.
Okay, before we go on, just give me a quick second because this speaker has